In the first set of examples for this video, we're going to look at 2, 4, and 6, and in these we are to determine whether the function is a power function given that c, g, k, and pi are constants. So for those that are power functions, we are to state the power and the constant of variation. Alright, remember, for a function to be a power function, the only requirement is that it can be written as k times x to the a, where k and a are non-zero constants. And k is your coefficient and a is your exponent. So we're simply verifying that we can follow that format, and we see the format here directly on number 2. So this is a power function. Let's try that again. Power function with k, which is the coefficient, 9, or also known as the constant of variation or constant of proportion, and our exponent, or our power, is 5/3. So then we go to number 2, which we could write it as 13 times x to the 0, which would follow the general description kx to the a, but this one fails because k and a have to be non-zero constants. 13 works for us because that's non-zero, but 0 is clearly not non-zero, so we would say this is not a power function because a must be non-zero. And then if we look at number 6, it looks a little confusing, but again, don't be intimidated and don't make big judgment calls without thinking in detail. You don't need to worry about this weird notation on the function. That's just the function name. Your focus needs to be on the right hand side. So here we have 1/2 kv to the 5th power, and this would not be a power function except for the fact that in the directions we were told that k is a constant, so that just makes the 1/2 k our constant of variation, and we do have a non-zero constant of variation and a non-zero power, so this example is a power function with constant of variation and I'm writing it out because it's just weird to say k is 1/2 k. That doesn't seem right. Our constant of variation is 1/2 k, and our power is 5. And then on the next set, we have a similar set of directions, but a significant change in what it is we are determining here. And that is, for this set, we are to determine whether the function is a monomial function. And in this set, L and pi represent constants. And then for those that are monomial functions, we are to state the degree and the leading coefficient. And if they're not, we are to explain why they're not. Alright, so on number 12, we have 3x to the negative 5. But to verify that we've met the requirements, again, we have to think in detail about what a monomial function is defined to be. And a monomial function does look a lot like a power function, but now we have a new requirement, and that is that k is a constant and n is a positive integer. Now, you have to be careful about this wording, because in the definition as it was given, you have f of x equals k as a possibility. And remember, in that instance, so if you went back and looked at number 4, then we could say that it is a monomial function, because for this set, you technically can have a 0 exponent. So be aware of that, although we don't have that in any of these examples. Alright, but let's look at number 12. We have f of x equals 3 times x to the negative 5th power, and the requirement again is that our constant can be any constant. So that changes from the definition of a power function, because a power function says that they have to be non-zero constants, both k and a. But the monomial function says k is just a constant, so it could be any number. So definitely 3 meets that requirement. So k equals 3, and our n, as it's called in the monomial function set, is -5, and the requirement for our exponent is that we would have a positive integer, so then we determine that this is not a monomial function. So let's move on to number 14. Again, it follows the general shape of a power function or a monomial function when you first glance at it, but you have to think in detail to be able to decide whether or not this is a monomial function as we're assigned in this set. And again, k is a constant is the only requirement, so our -2 meets the requirement. And so then we look at our n, which would be the exponent, and the problem we have here is that if this was x to the 5th, it would be, yes, a monomial, but since it's 5 to the x, our n is x, so this is what eliminates this one from being a monomial function. So your reason that it's not one, oh, and we didn't give the reason on 12. I'll go back and do that one after we finish this one. But a must be, or no, I'm sorry, we have to call them n in this set. N must be a positive integer. Well, obviously x is not an integer of any description, so that means that we do not have a monomial function. And we'll abbreviate that here. And go back to 12 and give our reason there. -5 is not a positive integer, is the reason for 12. And now we'll look at 16. And again, the directions did tell us that L and pi represent constants. So here we have our good friend, the area formula for a rectangle. And we can make this more explicitly what it is by putting a 1 in as our exponent on the w, because then we could say that our constant of variation is L, which was told to be constant in this set of problems, and then w to the 1 power tells us that our n is 1, so this is a monomial function. And then for our next problem, number 18, we have a set of directions for this. In fact, we're going to do 3 of these, 18, 20, and 22. We're to write the statement as a power function equation. Use k for the constant of variation where 1 is not given. So in number 18, we are given that the volume V of a circular cylinder with fixed height. Now, you have to be careful. You don't want to be too cavalier about doing these problems, because in this problem it specifies that the height is fixed. So that makes the height a constant. Is proportional to the square of its radius. So the volume is proportional to the square of its radius. So we're going to put k as our constant of variation and r squared. And that might bother you to write that in this format, but let's look at it from this perspective. If we took the volume formula for a cylinder, which would be pi r squared h, we have just been told by this problem that our, let me pick a color here that's going to show up on this background. I'll go white, that'll be obvious. Alright, we know pi is a constant, and we were just told that h is a constant. So for our definition, just to write explicitly as a power function, then we wrote it with kr squared. But in our problem, we should know that k would be equal to pi times whatever this constant height is. And so that is the correct answer for that one. All right, and then on to the next one. We have Charles' law states that the volume of an enclosed gas at a constant temperature varies directly as the absolute temperature T. All right, so all that wording at the beginning, Charles' law states the volume V of an enclosed gas at constant temperature. That's literally boiled down to V for volume. And then varies directly just tells you that your K is going to multiply the absolute temperature T. So that's just V equals KT. Then on number 22, we are given that the speed P of a free-falling object that has been dropped from rest varies as the square root of the distance traveled d with constant of variation k equals the square root of 2g. All right, so P varies, and this, I tell you what, let's underline the significant things we're saying here. The speed varies. All right, so we want to jump over all that stuff in the middle, because to write the formula we don't even need all that. Varies as the square root of the distance traveled. And then we have this constant of variation defined as the square root of 2g. So we're going to write P, and it says it varies. So that verb there tells you that that's where your equation is going to break. It varies how? It varies with constant of variation, and since we're used to putting that first, we'll write that first even though it was written after the variable, which is the square root of our variable d. So this is what you would have as your uncleaned up equation, but then as your final answer you would write the square root of 2gd. Then we're going to number 24, and on 24 and 26 we'll do two examples of this to end this video. We're going to be given the equation, and then we're going to write the statement that we would interpret that equation to represent. So on 24 we're given that C equals pi d, and that's a pretty well-known relationship, where C and d are the circumference and diameter of a circle, and pi is the usual mathematical constant. And that is your author's wording, not mine. I thought that was pretty stiff and funny at the same time. Anyway, let's write this sentence. So we're reading from the equation itself, but we have to write a sentence, we have to know what C represents. So the circumference is what C stands for. And then to choose our verb, we have to look at the other side to see how it varies so that we can word our sentence correctly. And we could say is, but that would be harder to word if we don't say varies. Or use the other way to say that. You could say the circumference of a circle, and let's go ahead and say that. I would be okay if you left the of a circle off, but let's be really careful and correct here. The circumference of a circle is proportional to, so I can switch up my wording some, the diameter, okay, try that again, board lost touch with my hand there for a minute, the diameter with constant of variation pi. And this just demonstrates that you understand the structure of the sentences well enough to work either from the sentence to the equation or from the equation to the sentence. Then on 26, we've got d equals p squared over 2g, and we are to write that as a sentence. And just to cover what the variables represent, d is the distance traveled by a free-falling object dropped from rest, p is the speed of the object, and g is the constant acceleration due to gravity. So, we're going to, again, you start with the left side and say, the distance traveled by a free-falling object dropped from rest varies directly and remember, varies directly just means you can multiply one of the variables by some constant and get the other variable with the square of the speed of the object with constant of variation my O did not form properly. Constant of variation 1 over 2g. And in case that's not obvious to you, sorry about that, in case that's not obvious to you, remember that you could rewrite this problem as it was described as 1 over 2g times p squared to make it more obvious what the connection is in the variables and constants in this problem. And that is the end of this video.